Let's do another example of finding the average rate of change using the formula. So here we're given the function L of x is equal to 2x minus 7. It says find the average rate of change between these various portions. And then it asks, do we notice a trend? So let's just go ahead and start doing some math and see what we end up with. So here, notice that our function is L of x. So we can always adjust the average rate of change formula to, remember f is just an arbitrary letter for function, but you can always change that to L. So here we'd have L of 7 minus L of 2 divided by 7 minus 2. So it doesn't always have to be f. F is just what we usually use for functions, but sometimes we use other things. So whatever, it doesn't matter. Anyways, it's always the values, the difference in the values divided by the difference in the inputs. So L of 7 here, if we plug in 7, we'd have 2 times 7 is 14. 14 minus 7 would be 7. And then be minus 2 L of 2. Plugging in 2 would give us 4 minus 7. That would be negative 3. And with negatives, reminder that it's always the first thing minus the second thing. Sometimes some of those function values could be negative, which would create a double negative. And as we know, a negative times a negative makes a positive. So we got to be careful with our negatives not to lose them, because in this case, it's going to end up becoming 7 plus 3. And that's, of course, divided by 5. So we'd have 10 divided by 5, which is 2. And that would give us our average rate of change on this interval. Cool. This one's pretty easy because the function is not so complicated. So let's look at a different interval and see if we can pick up on a trend. So between 0 and 1, that would be L of 1 minus L of 0 divided by 1 minus 0. So L of 1 would be 2 times 1 is 2 minus 7. 2 minus 7 is negative 5, which would give us L of 1. And then we'd have L of 1 minus L of 0. L of 0 is going to, remember, well, the 0 value of a function is always the y-intercept, which in this case would be negative 7. Because if I plug in 0, that's just going to go away because 2 times 0. And so that would be negative 7. Again, I need to have a double negative here. Going to make sure to use parentheses to make sure I don't forget that. And that's all going to be divided by 1. So this would turn into negative 5 plus 7 over 1. That would be 2 over 1, or 2. So it turns out that my average rate of change is still 2. And this could be a little strange because, like in the previous example, the average rate of change was different depending on where I looked. But if you actually look at this equation, notice that it is a linear function, which is probably why I named it L. But it has a consistent slope and y-intercept of negative 7. And it's mx plus b. So if you recall, the slope of a line is always determined by m, the coefficient on your x term. And basically why I look at this example is because it should not be surprising that our average rate of change is 2, because it's a straight line. And if we look at the graph of that straight line, it would have a slope of 2 and an intercept of negative 7. No matter what points I pick on this line, if I connect any 2 points on the line together, the slope is always going to be 2, meaning that the average rate of change should always be consistent because it has the same slope always. And this is just something that we can kind of check to make sure it works. Whereas any line that has curvature, the average rate of change will change depending on where I pick. Now, the last one to look at here is what if we picked, excuse me, a and a plus h as our intervals. This seems a little strange because so far we've only been looking at what happens if we plug in numbers into functions, but actually if you plug in even these algebraic expressions, it will still work. And this is actually good practice for the difference quotient, which we're going to start working on this week as well. So let's go ahead and plug those into our average rate of change formula. And let's see what happens. So again, this is going to be like B and this is going to be A. So I'm going to plug in, it's always f of B minus f of A over B minus A. So I'm going to have A plus H minus A. Basically on the bottom, I just have the difference between the boundaries. Try to make that a little bit better. And then on the top, it's going to be plugging them into the function. So basically this whole thing goes into L minus L of A. And yeah, so I've got the setup started. Now, the question is, how do I proceed from here? Well, the denominator, all we have is A plus H minus A. Algebra would tell us, well, A and A minus A, those are like terms. Those would actually cancel each other out because A minus A would make 0. So the denominator actually would just simplify down to specifically H here. And the numerator, well, L of a plus h, that means we can always calculate that on the side, which is what I usually recommend doing for the difference quotient, which we're going to get to. That just means take my function. Well, the function was L of x is equal to 2x minus 7. So I'm always going to take 2, multiply by my input, and then subtract 7. Here, though, the input is a little bit more complicated, so I want to make sure that I substitute that whole thing in for x. And that's how, like, if you're wondering how do I plug in something other than a number into a function, it would just be algebraic substitution. You're going to plug that in for x and use proper algebra technique to simplify. So like from here, we would of course have to use the distributive property because we have 2 times an entire a plus h. So this would give me 2a plus 2h minus 7. And that would be what this is, L of a plus h. So in my numerator here, I'm going to have 2a plus 2h minus 7. And that is the first component. And then I should take away minus L of a, which is that part of the function. Notice I use parentheses just to make sure that when I'm subtracting functions, I'm always subtracting the whole thing, just as I use parentheses around the negative above. So now what is L of a? Well, L of a is, L of x is just, if I plug in x, I get 2x minus 7. It's just instead I would substitute a. So basically we just change x to a, and that would leave me with 2a minus 7. And that would be L of a. So these examples tend to get a little bit more confusing because we're not always used to doing algebra in this way. So I'll try to be quite clear about how I got each part. The first part is from here. I plugged in a plus h into my function and got that. The second part was by plugging a into my function and I got that. I need to still subtract them, so I still have yet to do that. And then on the bottom, I just simplify by taking the difference of this and this. Okay, so in the next step, let me erase a lot of this extra stuff that I've been writing. Now I want to simplify to see what happens. So actually notice that, again, I would have the distributive property apply here because I have minus an entire polynomial. So I'd have 2a plus 2h minus 7. Then it'd be minus 2a plus 7 because the negative would distribute to both terms. And all of this should be divided by h. And what you probably notice about the numerator here is that, well, I have a minus 7 and a plus 7. Those will cancel. And I have a 2a and a minus 2a. Those will also cancel because they are like terms but opposites, which will always add up to 0. And that will leave me with only 2h divided by h. Notice that I actually end up with a common factor of h, which will also cancel because anything divided by itself makes 1, which would leave me with 2. And what I end up getting is 2. So what this is sort of saying is it does not matter where I take my average rate of change, I'm going to get the same slope regardless. And since this is a straight line, it makes sense that this should happen. Now, with most functions, this will not happen. But actually, this sort of technique is how we generalize the process of finding slope in an algebraic way. That's what the idea behind the difference quotient is in the next video.